Hey everyone, I'm Xiaoyu. Today I'm going to introduce our recent work for open vocabulary 3D scene understanding. So basically, I did this work during my internship at Google. So the task we are exploring is the open vocabulary 3D semantic understanding. But our work is different from the previous methods because all the previous state-of-the-art models, they rely on the clue-based features, but we are trying to explore an alternative way, which means we are trying to fine-tune a text-to-image diffusion models as a feature encoder. About the problem description, we are investigating the use of diffusion models, which are pre-trained on the large-scale image-text pairs for the open vocabulary 3D scene understanding. And for the inputs to our model, it contains two parts. The first part is a 3D scene representation, and here we are using a point cloud representation. And the second part is a post RGB images. It's like a multi-view images correspond to the 3D scene, but we have the camera poses and the depth information. The good thing of having such camera information is we can find the point pixel correspondence. For example, we can know that, okay, this green point in the 3D scene should correspond to this pixel in the 2D image. We can have such pixel point correspondence between the 2D and the 3D space. And for the open vocabulary 3D perception task, there are multiple downstream tasks. The first one is called the open vocabulary 3D semantic segmentation, which means we are trying to assign a semantic label to each of the 3D point. And here we also explore a more challenging setting, which is called the long-tailed semantic segmentation. It's like some of the categories may not commonly appear in daily life. So for example, one of the rare classes is like the soap dispenser. And this is for the open vocabulary semantic segmentation. And the second downstream task is called zero grounding task, which means the user may not just give a single category as the text query. Instead, they may give a complicated text prompt. And this text prompt may describe the key objects, the shape, appearance, or color of the key object, like the square green chair, or it could describe some special relationships, like find the white sneakers that are closer to the desk chair. Which means for those complicated text prompts, it will require the model to reason about the spatial relations. And because the open vocabulary 3D perception is a very new area, so there are still many different problem formulations for this task. And here I will introduce two of the representative work in the 3D perception. The first work is called Open Scene. It's published in CVPR 2023. So basically, it takes two types of inputs, as we discussed before. The first one is a multi-view RGB images, and the second one is a 3D point cloud. And the model contains two branches. The first branch is a 2D feature encoder. It's frozen. This model uses the clip feature encoder. So basically, they can extract the clip feature representations for each of the RGB images. And for the second branch, it's a 3D branch, and it takes the 3D point cloud as input. They train a 3D backbone to predict the 3D representation. And as we discussed before, we know the one-to-one correspondence between the pixel and the point, which means we can train multimodal distillation loss to force the point level feature representation between the 2D and the 3D to be closer in the feature space. So in this way, we can use the distillation loss as a training target to train the 3D UNet backbone. And during inference time, the model combines the semantic prediction from the 2D and the 3D branch and fills the fills the model predictions to compute the final label. The second representative work is called Open Mask 3D. It's different from the previous one because it's a training-free framework. So basically, it takes the point cloud as input and the multi-view RGB images. For the 3D point cloud, they leverage a pre-trained off-the-shelf 3D mask proposal network, which means this mask proposal network is borrowed from some pre-trained networks, and but to train this network, it requires some annotated 3D masks. So by leveraging the mask proposal network, the model is able to get a set of 3D masks. But here we may note that those masks are class agnostic, which means they don't contain any semantic information. We don't know what the object is for each of the masks. So in order to know the semantic information, they leverage another 2D branch, which takes the post RGBD frames as input. And again, they use the clip-based feature encoder. But different from the previous work, which leverages a distillation loss, they are doing some training-free operation. Specifically, they are trying to use average pooling, like to pull the feature representation from the 2D clip feature. For example, they know, okay, this part, this green part should correspond to a foreground object, and then they can pull the feature representation from the 2D clip feature. And then they average all the feature representations within the mask to get the final semantic embedding. And finally, during inference time, given a text query, they can compute the cosine similarity between the text embedding and the mask embedding, and they can select the masks with the smallest, with the closer distance as the final mask prediction. So, previously we discussed the 2 of the representative work, and next I will introduce our framework, and in the high level, how our framework is different from the previous methods. Here, A is the OpenSync framework, which means it adapts the point-wise distillation loss. Like it has 2 branches. The first one is a clip branch, and the second one is a twin 3D model. And they are trying to force the feature representation between the 2D and the 3D space to be closer. And the second one is the OpenMask 3D, which means it's a training-free network, and they are doing a mask pooling to pull the feature representation from the clip model based on the mask predictions from the 3D proposal network. And in the final figure C here, we show the overview of our proposal method. So our model is different from the previous methods in the following 2 perspectives. First, we are leveraging a stable diffusion backbone, which means it's different from the clip-based features used in A and B here. For the motivation about why we want to explore stable diffusion, the first one is we think that for the clip-based model during its pre-training stage, it's trying to optimize for the global representation. For example, we have a text image pair, and the text is a dog runs on the grass, and we have a corresponding image for that. And the clue-based feature is like trying to compress the text as a single vector and compress the image as a single vector. And it tries to minimize the distance between two vectors. And we think that it might lose some localization information during the pre-training stage. But for the Stable Diffusion, because it's trained for a generative task, it's like from a very high level, it's like a mask and a reconstruction. So we think that maybe the generative pre-training objective is more suitable for the semantic segmentation because it may contain some localization information. This is our first motivation. And the second motivation is that there are some previous work showing the clue-based feature is not good at reasoning about compositionality. Like a text description could describe multiple key attributes like the object's color, appearance, geometry, shape, or some special relationship. But for the generative models such as Stable Diffusion, if we describe an object and its color also different attributes, we found that the diffusion model can at least generate such object. So we think that maybe the Stable Diffusion models they are more suitable for text prompts that require the reasoning of compositionality. And this is the first difference, which is we leverage the Stable Diffusion as a feature encoder. And the second difference is we are using a mask-based segmentation head. So for all the previous methods, it leverages the point-based segmentation head, which means they are trying to perform the distillation in a point level, like this point and this pixel should be closer in the feature space. But what we are trying to do is a mask-based distillation. And our motivation is that we think that the 2D branch is pre-trained on large text image pairs. So they should be suitable for reasoning about the semantics or predict the semantic levels. But the 3D branch should be good at predict the 3D masks. Because previously I did some very quick experiments. Let's say we have a 3D point cloud and we use some traditional clustering algorithm to predict the mask proposals. We found that even very traditional algorithms, which doesn't require any training, it can predict the class boundaries very well. I think it's because the 3D geometry is pretty helpful in the clustering process. So based on those observations, we are trying to decouple the learning of the 2D semantic embedding and the 3D mask embeddings. So specifically, we are trying to leverage the 2D branch, which contains a mask-based segmentation head to predict two things. The first thing is a set of 2D masks. And the second thing is the 2D mask embeddings. Like, okay, for this mask, it should correspond to the desk class or the table class. It's like a semantic embedding in the mask level. And for the second branch, we are trying to train a 3D segmentation model. It's a U-Net-based architecture. And it will predict the feature representation for the input 3D point cloud. But for this branch, we are trying to make it only predict the 3D masks instead of predicting the semantic labels, because we think they are for the 3D branch, it may not be compatible as a 2D branch in terms of the semantic prediction. So in this way, we have the 2D branch, it will predict a set of 2D masks and mask embeddings. And we have the 3D branch, which will predict the 3D masks. And we are proposing a multimodal distillation loss to force the 2D and the 3D branch to make consistent predictions. So this is a very high level overview of our framework and how our model is different from the previous methods. So next, I will go into the model details. And And we follow the setting of the OpenSync, which means we don't need any annotated 3D data. What we have is a set of 2D images and a 3D point cloud. And the 3D point cloud doesn't have any 3D annotations, so it's unlabeled 3D point cloud. So we have a 2D foundation model, which is a text-to-image diffusion model. We use Stable Diffusion in our work. So we first extract the feature representations using the diffusion unit. Like we use the feature representations from its upsampling layers. And then we can have a set of feature representations for each of the input image. And then we have a 2D mask generator. The mask generator will take the feature representations for each image and predict a set of 2D masks and also the mask embeddings. Again, the mask embeddings is like a semantic embedding that indicates the category for each mask. And for the 3D branch, it takes the 3D point cloud as input. And we use the UNet as a feature backbone. The output of UNet is a set of high-resolution 3D embeddings. And then we will compute the cosine similarity between the 3D embeddings and the mask embeddings. So it's like we are trying to compute an attention map. And the activated area, like the red area here, denote that it should correspond to a 3D mask. So in this way, we can predict the 3D masks from the bottom branch. And finally, we are using a multimodal mask distillation loss to force the 2D masks and the 3D masks to be consistent. For our entire framework, the text-to-image diffusion model is flawed. We are not fine-tuned, and also the mask generator is flawed. The only part we are fine-tuning is the 3D UNet architecture. And for the experiment, we perform the evaluation on different downstream tasks. The first one is the open vocabulary 3D semantic segmentation. We evaluate our model on the common categories, such as the ScanNet, which contains 20 common categories in the daily life, and also the Matplotlib 3D. And the second evaluation setting is more challenging. It's called the long-tailed semantic segmentation. And we do the evaluation on two datasets, the replica and the ScanNet 200. And finally, we also perform evaluation on the zero grounding task. The dataset we use is NR3D. So basically, we are trying to evaluate the model's performance on novel text prompts, like the user may describe some compositional information of the object, and this may not appear in the training data. And for the evaluation metrics, we report the head, common, tail, and the overall mean intersection over union for the semantic segmentation. It's mainly for the long-tailed categories. Because for the common categories, it's like all of them belong to the header class. And the second one is the accuracy for the 3D zero grounding task. And next we can check the experimental results. For the semantic segmentation benchmark, we observe that our model outperforms the previous methods. And also, another thing we observe that, like for the fully supervised model, there is still a very large performance gap between the fully supervised model and the zero-shot open vocabulary model. But what we observe that for the tail classes, which means there are some training data, but the training data for these specific tail categories have a very small number of the training data for tail categories. So specifically for those categories, we observe that actually our model can achieve a very comparable performance compared to the fully supervised methods. This may suggest that, like, if we want to deploy a model for real-world applications, but we know that in our test setting or the evaluation setting, there are a lot of tail categories, then we may consider to adapt models in the open vocabulary setting instead of to use some fully supervised methods. And next, I will visualize the semantic segmentation results. So basically, we show in the first row, we show the input 3D point cloud, and the second row, we visualize the ground truth semantic segmentation. The third row is visualize the OpenSing baseline, which achieves the top performance, and also achieves the top performance in all the previous state-of-the-art methods. And finally, we visualize the model performance of our proposed method. So we observe that our model is able to predict relatively accurate semantic segmentation labels in terms of both like the object category or the object boundaries. But we also observe there are some problems for all the open vocabulary baselines. For example, in the first column, we can see that both OpenSing and ours fail to predict the table class accurately. Instead, we are trying to predict it as a kitchen counter. So this is we also observe some similar problems. So like the open vocabulary perception models, they are not good at telling the difference of the fine-grained categories. Like the table and the kitchen counter could have very close semantic meanings. So it will be interesting to explore how to tell the minor difference between such fine-grained categories in the future work. And next, we show some visualizations on the replica dataset. So we observe that our model achieves a better performance than the OpenSing baseline. And next is like we are trying to visualize some semantic predictions for challenging categories. For challenging categories, we are meaning that it doesn't belong to the common categories, and it has a very small number of training data. So here we visualize several categories such as book, which is like a very small object, and vase here, and also the radiate and bench categories. So this also suggests that our model achieves a better performance in terms of the tail or some non-common categories, which also aligns with the numbers in the previous table. Finally, we visualize some real grounding results, and for the evaluation protocol, we have an input 3D point cloud and multi-view RGB images, and the user will give a text query, and the text query may describe the object's attributes like shape and color. And then we have a set of, for example, we could have 10 master proposals, and our task for the visual grounding is to select the one master proposal from all the 10 masks that correspond to this specific text query. It's like a ranking, but we focus on the top one performance. So here we found that compared to OpenSing, our model can localize the complicated text queries well. So for example, it could reason about the objects, the shape and the color of the object, and also reason about the texture of the key object, such as wrinkled, and also reason about the a special relationship, like the trash can next to the desk. And finally, it can reason about the usage of the keyword, like the blue waste basket possibly for recycling. So finally, I will discuss the limitations and the future work. So one problem we face during the model training and inference is the inference speed of diffusion model is very slow compared to the clip-based method. So we use some optimization method. For example, we are caching all the feature representations for the images. So which means we don't apply any on-the-fly data augmentation tool because it will require a very long time for the inference of the diffusion-based models. So in order to improve the inference speed, one of the possible ways to change the feature backbone, because currently we are using a UNet-based diffusion architecture. But recently, we may see that the transformer-based diffusion models achieve a better performance and it becomes more and more popular. So one of the ways to leverage the transformer-based backbone, which means we can apply different optimization methods for transformer, such as KV cache and and flash attention. In this way, we may be able to achieve some real-time inference speed. And the second limitation is because of the constraints of GPU memories. When we process the 3D point cloud, we cut it into different pieces, which means we can't fit the entire 3D point cloud into GPU. But if we consider that for some complicated text prompts, like it could require the spatial reasoning between two objects that are very far to each other. In this way, those two objects may not appear in the same split. Like when we split the 3D scene into multiple pieces, those two objects could belong to two different pieces. And in this way, it may not be able to handle some spatial reasoning text prompts. So in the future, more work could be done to, let's say, develop some efficient 3D representations, which means we can fit the entire 3D point cloud into the GPU memory and do some reasoning task. And the third one is exploring different diffusion backbones. So currently we can see that nearly for every week there will be new diffusion models. So it will be interesting to explore like the difference between diffusion backbones. Like will a UNet-based architecture lead to a better performance, or a transform-based architecture, or some autoregressive based diffusion architecture. So basically, we can see the diffusion model or the diffusion objective as a pre-training stage. And what we are trying to do is to fine-tune a generatively pre-trained architecture for different downstream tasks. And the downstream task is a perception task. So we can see there are some gap between the pre-training objective and the fine-tuning objective. So it will be interesting to say, for example, if the generative model achieve a better performance in terms of the generation quality, like the clip score or something, does that guarantee for the downstream task, for our perception task, will it also lead to a better performance? So like, I think I didn't say similar research before, but I think it will be interesting. Let's say we have a curve, and one axis is for the generation quality, and another axis is for the perception score. So we can maybe draw a curve and see whether these two are highly correlated, or there are some other factors like the model backbone or the training data will also matter in this curve. Yeah, I think that's all for my presentation, and I will be happy to take any questions. So if you have anything to discuss, either for questions for this work or you have any ideas for future directions, I will be happy to chat. Yeah, just feel free to drop me an email.
Fantastic. So there are three questions in the chat. Let me see if I can fish them out. The first one came during your literature review slide. So that was near the beginning. And the
Yeah.
question was, in this diagram, the app performs 3D image segmentation, meaning finding items in the text list. I guess that's the question. Is the app performing 3D image segmentation, finding items in the text list?
Um, yeah, I think I understand your question. Like, it performs. Let me go to that slide. So it performs a 3D scene segmentation. I'm not sure, like for the 3D image, does it refer to the 3D point cloud? I know sometimes people use that to refer to the same thing. But basically to clarify, those both of the two models, also for our methods is for the 3D segmentation, and the inference time is like the user will give a text prompt. I will have a yeah, I think for your setting, like for example, for the semantic segmentation, the user will give a set of like 200 categories, and what what we are trying to do is to find the masks that correspond to the 200 categories. Yeah, I think it's what you said is correct in this sense.
And
Like
then our
finding,
next, go
yeah.
ahead. I was just going to say that our next question comes during the model overview slide. And that question was, what are some of the real world applications of it and how long does it take for inference?
Yeah, I think that's a very good question. For real world applications, I think it's commonly used for robots like navigation or manipulation task. And how long it takes for inference? Yeah, I think currently the inference speed is uh, could be a bottleneck. Like the inference speed should be slower than the cliff-based model. But there are multiple optimization methods to optimize that. But currently, what we are primarily focused on is the model's accuracy instead of the inference speed. And I think for the inference time, I think for a single 3D scene, it should be able to be completed, let's say within 30 seconds. But I need to double check this number. But basically for a single 3D scene, you should be able to complete the reasoning or the semantic segmentation within 30 seconds on a modern GPU machine. The machine I use is 3090 time. But we can imagine that if for some real world applications that we may not have access to modern GPUs, like we only have to some edge device or mobile device, then I think that there are some work needs to be done to optimize the entire workflow as well as the model architecture.
And then we do have one final question in the chat, which is came towards the end of the presentation. Can the output of your system be used to construct a better 3D image that includes labels, segmented 3D objects, so that the 3D objects can be removed from the 3D image, and the diffusion can be deployed to fill in the space where the object was removed?
Yeah, I think that's a very good question. The answer is yes. We do see, and I like the idea you mentioned. I do see some recent literature in the 2D space, like we are trying to, for example, editing an image. We want to replace, for example, the table with a table in different color, or we want to replace the table with a desk. Then in the 2D space, they will also use the same to remove desk, which means there will be a hole left in this image, and then you can use diffusion model to do the inpainting. So I think I can also totally understand your question. In the 3D space, we can do the similar thing. For example, we can do the 3D segmentation, and we know that, okay, this part is a 3D model of the desk, and we can remove that and generate a new 3D asset and insert that into the same place. Yeah,
So
I think for your question, the answer is yes. Yeah.
Perfect. So then we have 2 additional questions in the Q&A. Why did you choose to use point clouds instead of meshes?
Yeah, I think that's a very good question. I have a recent I have another work which is published in CVPR 2023. It's using a mesh-based representation for the human action understanding. So based on my experience for mesh and point cloud, one thing is the mesh is represented as a set of vertices, and also the connections between vertices to form the faces like triangles. And I found that the processing of meshes is much slower compared to the processing of point cloud. And another thing is, I think if we sample the point clouds very dense, like it can cover, it's like we are sample all the points from the meshes, then basically I think they contain the same information, but the processing of the 3D point cloud will be much faster compared to the 3D meshes. Yeah, but I think it will be interesting to see if adapting the mesh-based representation could lead to a better performance in the 3D perception task. For my previous experience, like it's a different task, but for the human action recognition, you can understand it as a classification task. We do find that using a mesh-based representation is better than the point cloud-based representation, specifically for the human action recognition task. So yeah, it will be interesting to explore if the conclusion is the same for the 3D perception task. Yeah.
And then we have one final question in the Q&A, which is, have you considered using GANs instead of diffusion models in your model architecture?
Yeah, I think that's a very good question. So for the perception task, there are, like if we want to use generative models for perception task, then there are multiple ways to leverage that. One way is, like as we discussed, we can use it as a feature encoder, like we are extracting the latent feature representations from using the diffusion backbone. And another way is we can generate a lot of images. It's like we are leveraging the final output from the diffusion model. We are just, for example, we can generate a lot of 3D assets, or we can generate a lot of 2D images, and we are using them as a like a data augmentation method to increase the diversity of the training data. So I think for GAN-based method, I saw a lot of works for the second way. Like a lot of people have explored how to use GAN to generate a lot of RGB images, and they can, for example, improve the classification performance using the generated images. But I haven't seen, or maybe I need to double check the literature, but I didn't remember like there are some similar work, for example, extracting the feature representation from the GANs encoder and using that for the model performance. Yeah, I think one problem, like we know for GAN, is the training is not stable. Like because it leverages some adversarial loss. So from the intuition perspective, I'm not pretty sure, for example, could we directly leverage the feature encoder from a GAN-based architecture to do the perception task? Because I just feel like even for the generation task, the GAN-based model is very hard to converge. I'm not sure for the converged model whether the feature representation will be helpful for the perception task. But for diffusion model, we know that the training is much more stable compared to GAN. So maybe from the intuition perspective, it's much more suitable to leverage the diffusion-based architecture instead of a GAN-based architecture.